All right, so today we're going to talk about iterated integrals. I am going to go through this as a how-to, and I'm going to leave the why do we to you to look at in the book and in the PowerPoints for the course. All right, we're starting to become a little pressed for time to finish, so I'm just going to show you how these work. We've got basically, I'll give you a quick why. All right, we've got basically the situation here where we want to be able to find, now if you think of integrals in Calc 1, right, they represent the area under the curve. Now in the case of integrals in R3, we're not looking at the area under the curve, we're looking at the volume under the curve. So I've got you can see right here that I've got a surface represented by this portion of the elliptical paraboloid, z equals 16 minus x squared minus 2y squared. All right, and what we're really looking for when we do integrals is the volume that is contained below this curve, in this case along a rectangular region in the xy plane. All right, so I have this rectangular region here in the xy plane, and we can use the definition of the integral that we had from Calc 1, right? Which was the basically the Riemann sum type definition with the summations and the limit as I goes to infinity and all that fun stuff. And then we were looking at rectangles. Now we're looking at rectangular solids. All right, so if I pull this up here, you can see over the region, right, we're taking our rectangular region here and we're breaking it up into smaller rectangles and then projecting those rectangles up until they hit the curve. And just like in Calc 1, the more rectangles you make, the closer your approximation is going to be. So big fat rectangles, sort of got an idea. I can make them smaller, I can make them smaller, and I keep making them smaller until I have a good approximation of the area that we're dealing with. All right, and that ends up being, that is not what I want there. All right, that ends up being the idea behind the definite integral is a double Riemann sum. I'm going to let you all read about that, okay? It's not anything I'm going to test you on. All right, so when we, as a practical matter, right, when we do a double integral, what we need to do is take a look at, all right, what it means to do an iterated integral. All right, so if I have an area in the plane, all right, actually, I think this might actually be better with the book. Let me take a look here real quick before I start writing stuff down. Yeah, here we go. Okay. So you've got your midpoint rule. I'm going to let you read through all that and iterated integrals. Here we go. 1t, not 2. I misspelled that. All right, so the idea here is we have an area in the plane that is represented by that rectangle. All right, so we find the area of that. All right, so the area of that rectangle is going to be, pick either A, B, or C, D. In the case of the book, they picked C, D, right? So I think that was going this way, all right, along Y. So you take the integral from C to D of the function, you get that rectangle, and then you take the integral again of that from A to B, and that gets you your volume. All right, so we're basically doing the area of the base times the height, all right, in terms of the integration. All right, so you'll see as far as the iterated integrals go, and again, yes, I know I spelled iterated wrong. We'll just get rid of that. All right, anyway. What we're going to be doing is looking at what tends to be called double integrals, right? A to B, C to D, our function, f of xy dy dx. Now, how do I know which way to write these? Well, it depends which one you're doing first. So you're going to think of this, I'll actually do this in a different color, right? You're going to think of this as being broken up like this. All right, so whatever differential you're using on the inside has to correspond to the inside bounds. So these are bounds along y. And whatever differential is on the outside has to correspond to the outside bounds. So these are the bounds along x. All right, so if we take a look at a problem, I have a problem here. It's not a problem, it's an example. We'll see problems later. And it's this. I'm going to do the integral from 0 to 3, and then from 1 to 2. And my function is x squared y dy dx. All right, now in terms of the practical matter of evaluating these, we evaluate them the same way we do partial derivatives. If I'm taking an integral with respect to y, x is a constant. If I'm taking an integral with respect to x, y is a constant. All right, so hopefully at this point you've had enough practice with partial derivatives that you're kind of used to that concept. All right, so I'm going to, again, when we look at this, we always work from the inside out. All right, so I have to evaluate this inside integral here. All right, the integral from 1 to 2 of x squared y dy. So I'm integrating this with respect to y, so x is a constant. All right, so I'm going to carry this along with me. All right, so if x is a constant, this is going to be x squared, that's just a constant, times the antiderivative of y, which is going to be 1/2 y squared. Now again, we're evaluating this, right? This is a definite integral from 1 to 2, and then I've got the dx outside. All right, so again, I still have to work inside. I have to evaluate my definite integral first. So I'm going to have 0 to 3. All right, so I plug in the 2. I get, well, let me just write it down. All right, so I'm going to leave the x squared outside for the moment. So I get 1/2 2 squared minus 1/2 1 squared dx. All right, so that's going to be 4, so that's going to be 2. That's going to be 1, so that's going to be 1/2. So that's going to be 3/2. All right, so we have here 3/2, so that's going to be the antiderivative from 0 to 3 of 3/2 x squared dx. All right, so now I'm just doing the antiderivative of this with respect to x. All right, I'm running out of room here, so I'll come down here. All right, so that's going to be 3/2 times 1/3 x to the third, evaluated from 0 to 3. So that's going to be 1/2 3 to the third minus 1/2 0 to the third. That's a really bad 0. 0 to the third. So that's 27/2. All right, so that's the process. All right, you work from the inside out. So we've got the dy on the inside. So the first integral we take is with respect to y. X is a constant. You do the antiderivative, evaluate the definite integral, and then you're left with the outside antiderivative, whatever that is, dx. All right, you evaluate that, and you've got your antiderivative. All right, so now the question that I'm sure some of you are asking, if you haven't read ahead, is, does it matter whether I do dy dx or dx dy? Do I have to do it one way over the other? Well, we can test this out with this example. All right, let me just get a little more space here because I'm writing kind of big. All right. If I reverse the order of the integration, now remember, the bounds are associated with the variable. So these are the bounds for y, these are the bounds for x. All right. So if I swap dy dx, right, and make it dx dy, I also have to swap the integral signs out here. All right, so if I do this the other way around, my outside integral becomes 1 to 2. My inside integral becomes 0 to 3. All right, my function is still x squared y. And now I'm going to swap these, dx, dy. All right, so I'm still working on the inside integral first. Only this time, all right, I'm doing dx first, which means y is a constant. So I'm going to bring this over here. All right, I do the antiderivative with respect to x. Y is a constant, so I'm just going to put the y there, times the antiderivative of x squared, which is going to be 1/3 x to the third. And then that is getting evaluated from 0 to 3. And we are left with dy. All right, so antiderivative, whoop, I knew I was going to do that at some point. The antiderivative from 1 to 2, hang on a second, I have to cough. All right, so this is going to be 9/2, 2 squared minus 9/2, 1 squared. So that's 4. So I can reduce that down, so that's 2. So that's 18 minus 9/2. All right, and if we go 2 over 2, that is 36, minus 9 is 27. So we get 27 over 2. All right, so they were the same. Okay, so the question now is, does it matter what order you do the integration in? And the answer is no, with a caveat. In order for us to be able to swap the order of integration, you need to have a continuous function on the rectangle that we're looking at. All right, so in the case of this particular problem, all right, the rectangle that we're looking at is the rectangle where x goes from 0 to 3 and y goes from 1 to 2. All right, so the rectangle, just to get you used to this notation, right, the rectangle that we are integrating over, we would write this way: x goes from 0 to 3, so 0 to 3, by y, which goes from 1 to 2. So you'll see some problems written like this, where they give you the rectangle, and you have to decide on the bounds. All right, so we have a theorem. All right, and the theorem, which is attributed to a mathematician by the name of Fubini, which everybody loves that name. Okay, is basically just giving us the ability to swap the order of integration. All right, so if f is continuous on the rectangle, x from a to b, y from c to d, then when you take the double integral over the region, which this is a general way of writing the integral, right? The double integral over the region, dA, right? A representing the area in the xy plane. We can do a to b, c to d, dy dx, or we can do c to d, a to b, dx dy. All right. At some point along the way, as we're doing these, the word Fubini becomes a verb. All right. So you'll hear me say we can Fubini this particular problem, meaning we can swap the order of integration. All right. So as long as I have a continuous function, I can do this. So now the question now becomes, well, if I can do it in either order, does it matter what order I do it in? Okay, and essentially the way this comes about is sometimes it does, sometimes it doesn't. All right, some integrals, and you would have seen this in Calc 1, are difficult and complicated. And some integrals, again, you would have seen this in Calc 1 and Calc 2, I should say, are pretty easy. And sometimes when you set up a definite integral, doing it in one direction, let's say dy dx, is easy, where doing it in the other direction, dx dy, is really hard. So, as far as the order of integration goes, let's take a look at a problem here. All right, I've got the antiderivative over the region, or the rectangle in this case, all right, of this y sine xy. And then we say dA, right, because that's the area in the xy plane that we're integrating over. So the rectangle that we're looking at, for right now we'll call it a rectangle, is going to be 1, 2 by 0 pi. 0 pi. All right, so let's take a look at this for a minute here. Remember, when you're looking at one of these rectangles, the rectangles are always x first, y second. So if I were to take a look at this in the xy plane, right? xy plane, I would have 1 to 2 along the x, and I would have 0, let's say, to pi along the y. So I'm going to have a rectangle that looks like that. All right, and this is the region that I'm integrating over. All right, so now we have to make a decision here because we're not being told which way to set this up. All right, do I do xy, do I do dx first, dy second, or do I do dy first, dx second? All right, well, let's look at our options here. Okay, if I were to do y first, all right, take a look here, right? If I were to do y first, x would be a constant, but then I would be integrating y sine constant times y. So basically y sine y. All right, you've done this before. I'm sure you've done this before in Calc 2 when you learned integration by parts. All right, personally, I'm not sure I want to do that. All right, integration by parts is complicated. And you've got decisions to make there. So rather than having to make decisions, let's take a look at what would happen if I did x first. So if I do dx dy, then y is a constant. So now I'm just integrating a constant times the sine function. All right, since I'm just doing a constant times the sine function, I know I'm going to get a constant times negative cosine. Okay, so it's going to be easier to do this with respect to x first because I won't have to deal with that by parts integration. So I'm going to set this up. I'm going to leave a little space so I can write the bounds in. All right, my function is y sine x y. And I'm making a decision that I want to do x first. So dx goes inside, which means my x bounds go inside. dy goes second, which means my y bounds go outside. All right. Okay, so I'm going to do the inside integral first. So with respect to x, y is just a constant, so I'm going to throw that out in front. When I do the antiderivative of sine xy, technically I have a u substitution, right? U is xy, y is a constant, so that means I'm going to bring the y down, which means I'm going to end up with a factor of 1 over y. All right, then the antiderivative of sine is negative cosine xy. And then we evaluate that from 1 to 2 dy. All right, so 0 to pi. All right, so those go away. So I have negative cosine pi x. I'm sorry, negative cosine 2x. 2x minus, which becomes plus cosine 1x. Uh, 1y. Okay. I heard you yelling at me, I promise. dy. Okay. All right. So this is what I'm looking at now. All right. And notice, no more integration by parts. This is just straight trig. All right. So this is going to be, so when I take the antiderivative of cosine 2y, I'm going to get 1/2 sine 2y. So that's going to be negative 1/2 sine 2y minus, or plus, that's just cosine, so actually that is minus, isn't it? Wait, no, that's plus sine y. And then we're evaluating that from 0 to pi. All right, so negative 1/2 sine 2 pi minus sine pi. No, plus, sorry. Keep doing that. Plus, I see what's going to happen here. Let's do it this way. Plus. Getting my pluses and my minuses mixed up because I'm trying to think ahead here. Minus negative 1/2 sine 0 plus sine 0. All of this is 0, isn't it, right? Sine 2 pi is 0. Sine pi is 0. So all of this equals 0. All right? Which, just like in Calc 1, means that we have a situation where this curve is symmetric above and below the xy plane. Okay? All right, but that's the idea. So you have to kind of think a little bit ahead when you're doing these. Okay? Now, let's look at a consequence of Fubini. All right? There's a consequence of Fubini is if you have a function that can be factored. All right, so if you have, let's say, z equals f of xy, all right, and f of xy can be factored so that you have a function of x times a function of y. All right, so you have something that can be factored into a function of x times a function of y. Then when we look at the double integral over a region, of f of xy dA. All right, we can break that up this way. The antiderivative from a to b of g of x dx times the antiderivative of c to d of h of y, sorry. H of y dy. All right, so I have a little example here that I probably can't fit on this page, but we'll find out. Nope, not going to fit on this page. All right, so we'll go up here. All right, so if, for example, I have the double integral over a region of sine x cosine y dA, and my region is 0 to pi over 2 for x and 0 to pi over 2 for y. All right, I can notice this is a function of x and y, right? That's multiplication there. All right, but sine x is just a function of x and sine y is just a function of y. All right, so if I look at my whole function as the product of a function of x and a function of y, I can split this up into two integrals, right? Sine of x dx times the antiderivative from 0 to pi over 2 of cosine of y dy. All right, then I just evaluate those two integrals and multiply them together. All right, I'm going to stop this video here, and I'm going to continue the second part of this in a new video.